have the two branches.
Like here, we are talking about this.
Yeah, not the root locus, but just the real part versus the parameter.
Okay, this here. This here you have lambda, and here you have the real part.
Yes.
Okay, and in this case you have 0 everywhere
Until the critical value.
and then this is the real part. Okay, the imaginary part here we are talking about the first root. This is nothing to do with bifurcation, nothing. Okay, this is also known in aeroelasticity. This is a standard plot, also known as bougie plot. You are plotting the real and imaginary part of your poles as a function of your parameter. This is standard in aeroelasticity, but this is not bifurcation. Absolutely. Okay.
Okay. I'm sorry for my words.
No. You are not alone in the world with this confusion in the mind. There are some teachers and professors having this kind of a confusion, but not me. I'm working in maybe 30 years about this field, and I can guarantee that this is not a bifurcation. Okay, so if you have the real part to be plotted, you have excuse me. Okay, you have this trend and then this trend here, and for the imaginary part you have an increasing value. So you start by this value, and then you have the imaginary part variate and then a stop. So you have this increasing, and here you have something like stabilized. Okay. So what you can see that your pole is variating the real part and its imaginary part. So you are variating the frequency.
Yeah.
The frequency of oscillation of the panel is actually variating with the aerodynamic flow increasing. Okay. After the critical point, the frequency is stabilized.
Okay.
And you have a couple of mode in sense of aeroelastic mode. You have, after the critical value, you have this pole and this pole. This pole is stable.
Yes.
But this is unstable. And this unstable value will give you a oscillating diverging solution.
Yes, clearly.
And this is the expectation by linear theory, period.
Okay.
Of course, look, this is important. What I'm saying now is important. This is the expectation of linear theory. Probably the oscillation will be given by this envelope in time. And this frequency, this period here is the imaginary part of the pole. And this coefficient of the exponential is the real part of the pole, okay?
Yes.
This is the prediction of the real theory. But in practice, when the output is growing higher and higher like this, at this level of amplitude, the nonlinearity promptly wake up. Oops, I am the nonlinearity. You are too high for me. So I have to be present in your simulation. Okay? But at this level, you have to rediscuss all your model. You have to include the nonlinearity. You don't include the nonlinearity in your model, but you should. This is an important point. Please hear me. If you considered the nonlinearity, at this level, if the nonlinearity are good nonlinearity, your solution will be kept at this level, always. You will have a limited solution. And this is threshold here is ensured by the nonlinearity. The nonlinearity are stabilizing. And this is the reason why in the reality you will see limited solution always, because that was your lucky day, and the linearity will show you a limit cycle, a so-called limit cycle. What is the limit cycle? The limit cycle is an oscillation characterized by the linear predicted unstable mode, which is limited in the reality by the nonlinearity. Okay, so crossing your stability limit, the system tries to go higher and higher response, higher and higher, but the stable part disappears. We are only the unstable, which want to be higher and higher and higher, but the nonlinearity wake up, oops, be cool, man, cool, and the nonlinearity is able to limit your oscillation in the so-called limit cycle. And as a final conclusion, this is the reason why you can see flutter. You can see a flutter instability. Remember what I showed you? I showed you this. Remember? For example, I showed you this. Look, this is important. So I want to use time for show you this point. I showed you this movie, and when you see this movie here,
Yes.
when you see this movie here, it's, oops, this is an oscillation. This is an oscillation with a frequency. So what I'm seeing a pole in the exact imaginary axis, a pole there in the imaginary axis before crossing. Just a picture, an exact picture when pole equal to j omega flutter. I can't believe in that, because in the reality, how can I be sure to be exactly on the imaginary axis? Probably you are further, you are after this limit, and you are in the lucky day because the nonlinearity are able to limit this oscillation in a limit cycle. So what you see in the reality is a limit cycle oscillation.
Okay. The stabilizing effect, as you said in the first lesson.
Right. Because I can't believe that you are a so good experimental man able to fix your parameter exactly
At that frequency.
Yes. Okay?
Okay.
What we learned now is one of the most important issues to be learned in aeroelasticity. And this is the limit, and this is the role of the linear analysis with respect to the nonlinear analysis. With the linear analysis, you will discover, you will determine the limit, the margin.
The margin of stability.
The flutter velocity, the lambda flutter velocity or the airspeed velocity can be evaluated by the linear theory. After the limit of the determined by the linear theory, after this value, the nonlinear oscillation are present, because when the system is going up and grows, you are activating the nonlinearity, surely. So after activating, if you activated the nonlinearity, if you do this, then if you activated the nonlinearity, let me redo this picture. I'm not able to cancel this line down here. I am disparaded. Okay. However, if your system is linear, you will have this response, and so on. Okay, with this equal to e to the power real part of s by t, and this frequency here, period equal to 1 on frequency, you have that this frequency, this omega is equal to 2 pi f, and this omega is the imaginary part of S. This is the linear theory. After the pole determination, you can predict this. If you have this is linear, and the nonlinear, I am not able to change my red. Incredible. Okay, the nonlinear is something like this. After this threshold level, the linearity are able to be activated, and then you have this amplitude for your oscillation. So this is linear and this is nonlinear. And this is what you see in the B-52 movie. So the frequency you can see is actually the flutter frequency. And the limit after that this solution is given is the flutter limit. Okay? Okay, so this is the discussion about bifurcation, the meaning of bifurcation. In the bifurcation theory, the bifurcation is another story. It's nothing to do with this. Okay? The bifurcation is the bifurcation of the nature of equilibrium solution. The number of the multiplying of the number of the equilibrium solution, period. And it happens for nonlinear systems, period. Now we are studying linear one, okay? Go back to linear system, okay?
Okay, thanks for the lesson.
No, I have to go back to the lesson, please. Okay. 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 No, okay. Now we have this polynomial of fourth order, complete with the odd term s to the power 3 and s to the power 1. Now, the problem of the study of searching of stability margins consists of determining the critical value of lambda, also known as S-flutter, and the critical value of the pole crossing. If the pole is crossing, the pole is pure imaginary, so the flutter pole is, whenever it's crossing, of type J omega F. So these two are the unknown when you are searching for the stability margin. Okay, and this is the problem I want to face with you, and probably you face this problem in your control theory course. Okay, so essentially we want now to study this generic situation. Here, I have here S flutter equal to J omega flutter, and this occurs for lambda equal to lambda flutter. So the unknown are lambda flutter and omega flutter. How many unknowns? Two unknowns. Can we have two equations for solving these two unknowns problem? Yes, we have always. Always. These two equations are obtained by the characteristic equation when you imagine, when you impose to have a marginal pole, a pole of type J omega F, and then instead of imposing all the characteristic equation as equal to 0, you separately impose the real part of the characteristic equation equal to 0 and the imaginary part of the characteristic equation equal to 0. So that's the two equations useful for determining these two parameters. Okay? This approach is very useful for characteristic equation of polynomial type. Indeed, in the case of polynomial, look this, I have to substitute here, instead of S, J omega flutter, because I want to imagine my root locus in the margin. And what happens? I will obtain the following. I will obtain S to the power 4, I will have omega flutter to the power 4. And of course, I have to involve all the even power of S as a real part. Because when you have S equal to J omega, when you have this, and you take the power of S, only the even powers give you real part. And this is the first contribution. Then you have another contribution of this multiplied by omega 1 square plus omega 2 square plus zeta 1, zeta 2. Okay? This is given by this. I am separating this part, and this part as real part, of course. And so I have to add also plus omega 1 square, omega 2 square plus lambda square, and plus J, and next the imaginary part as given by the odd power of S. And so we have J, or I if you prefer, minus zeta 1 plus zeta 2 omega flutter to the power 3 plus, and this is given by the third order power here, this, and then I have this as the first power of S to be included in the odd or imaginary part. So I have to include only the zeta 1 omega 2 plus zeta 2 omega 1 square by omega flutter equal to 0. So you have a complex number separated in real part and imaginary part. Oh guys, this happens only for polynomials. If you have a characteristic equation which is not a polynomial, you are in the unlucky day. What means polynomial? When you have polynomial? You have polynomial when your time equation is an ordinary differential equation with first order, second order derivative. If you have something complicated, for example, a time delay, for example, a delay mechanism, in that case, your characteristic equation should be some more complicated. Okay? I am anticipating job. So this is an easy case. This is a standard case. You should solve this exercise in your past control theory course. No problem. Because in control theory course, you study only ordinary differential equation, essentially. Regulating your system. Describing your system. So in this case, this is a method which is quite acceptable for analytically determining your margins for stability. What about your margins? So the margins are represented by lambda f and the frequency of the oscillation, of the unstable oscillation. Okay, imaginary part equal to 0. This is the real part. So this is the real part. And this is the imaginary one of my equation. Okay, is for everybody clear at this point? This is a very important point. Impose the imaginary part equal to 0. Then we have that you can look here, you can determine your omega flutter. You can simplify this cube and this omega f, and you can directly determine omega flutter square equal to zeta 1. Yes, zeta 1 omega 2 square divided by zeta 1 plus zeta 2 and plus zeta 2 omega 1 square divided by zeta 1 plus zeta 2. Interesting. I have imposed this equal to 0 and I obtained this. So the flutter frequency is something like a combination of the square of flutter frequency, better. It's just like a strange combination of omega 1 square and omega 2 square. And the coefficient of this combination is driven by the damping, the relative damping. Interesting. Okay, so just this is a weighted quantity. Okay, and so you can write this in this way: omega 1, alpha 1, excuse me, omega 2 square plus alpha 2 by omega 1 square, where alpha 1 plus alpha 2 is equal to 1, and are exactly this quantity, alpha 1 and alpha 2. Okay, so I rewrite this quantity better here, alpha 1 omega 2 square plus alpha 2 omega 1 square. Okay, I finish as concerning because all these quantities are known, so this is my flutter frequency. Okay, finished. What about the lambda? I can obtain lambda by the real part, by imposing the real part equal to 0. Okay. And imposing this, I have the square omega flutter by this equal to 0. And so I have minus omega flutter square, which I have determined, I've just determined, and plus I rewrite the quantity, and now I have here a bit of algebra, very stupid algebra, too, but I will develop this algebra with you, no problem. Zeta 1, zeta 2, and omega f to the power 2, minus omega 1 square omega 2 square. This is just this expression here. Now, note that this quantity is the product of the two dampings, so it's a very small quantity because zeta is a small number. So the product is a higher, small number. And then I can move this quantity in the apart in this expression, and therefore what I obtained is the following quantity. I want to write minus omega flutter to the power 2 minus, I have omega 1 square plus omega 2 square omega flutter to the power 2, and I also want to include this term, so I include also plus omega 1 omega 2 square. And at the end, I want to put aside the term plus zeta 1 zeta 2 omega flutter square, and I want to develop this quantity. This quantity is currently given to me the lambda square flutter limit as a function of omega flutter and omega 1 and omega 2. Okay, it's trivial. I want to a bit manipulate this quantity. In particular, here, this part in this bracket can be further developed just this way. I can write that quantity in this way: minus, look, omega flutter square by omega flutter square minus omega 1 square minus omega 2, multiplying again omega flutter square minus omega 1 square. If you look, it's very trivial. What I did is exactly to put in evidence this together with this term. You have an omega flutter here and here, and apart I have put in evidence this term with this term here. I perform this operation and I obtain this. This is the term I have put in evidence. Okay, and of course I have plus zeta 1 zeta 2 by omega flutter to the power square. So of course this is common with this, and so I can write minus omega flutter square minus omega 1 square by omega flutter square minus omega 2 square. Okay, plus zeta 1 zeta 2 omega flutter square. Okay, do better. Omega flutter is the term here. Omega flutter is this. So substitute this value for omega flutter, and we have minus. Here we have alpha 1 omega 2 square plus alpha 2 omega 1 square minus omega 1 square. And this is omega flutter square substitution. The same here. I have omega 1 omega 2 square plus omega 2 omega 1 square minus omega 2 to the power 2. Okay, plus zeta 1 zeta 2 omega flutter square. Okay, now remember that alpha 1 is equal to 1 minus alpha 2 by definition. Okay, by this definition here. And so if you substitute here alpha 1, and here too, so you substitute alpha 2. Alpha 2 is equal to alpha 2, excuse me, minus alpha 2 is equal to alpha 1 minus 1. You can apply these two formula here and here. You easily obtain this minus alpha 1 by omega 2 square minus omega 1 square, and alpha 2 omega 1 square minus omega 2 square. Interesting manipulation. And then zeta 1, zeta 2, omega flatter. Note that I don't want to substitute omega flatter here because this is a very small contribution, small, with respect to the rest of this expression. Okay, okay, almost finished, because here we have alpha 1 by alpha 2, okay? And therefore, lambda flatter square is equal to alpha 1, alpha 2 by omega 2 square minus omega 1 square plus, okay, plus zeta 1, zeta 2, omega flatter square. Small, this is small. Okay, what about alpha 1 by alpha 2? Alpha 1 by alpha 2 is alpha 1 by 1 minus alpha 1. Interesting equation. Is this. This is minus alpha 1 square by plus alpha 1. And this is 1, and this is 0. And here you have a maximum of this parabola for 1/2. And the maximum is given by the value of this quantity, which is 1 minus 1/4 plus 1/2, which is 1/4. Very stupid, but this is the situation. And what is alpha 1? Alpha 1 decides the distribution of the damping. If alpha 1 is 1/2, also alpha 2 is 1/2, and you have the same quantity of damping for the first mode and the second mode. Okay? So what alpha 1 is the dispenser of damping in the two modes. Okay? And so how can I read this formula? I can read this formula in this way. I'm almost finished. The square of the flutter limit is given by, mainly dependent on this first quantity, and here a secondary quantity here. In the first quantity, this first quantity is maximum if alpha 1 is equal to alpha 2 is equal to 1/2. So this quantity is maximum if the two damping are the same for each mode. If you are able to distribute your damping in equal part to your system, this is the best for flutter, because you are actually moving the flutter limit forward as possible, because this quantity is maximum. Okay? But this is not the only discussion to have with you about this parameter. So when when alpha 1 is equal to alpha 2 is equal to 1/2, okay, the quantity alpha 1, alpha 2 is maximum with respect to alpha 1. So this is the best situation for instability, because you are moving your stability higher, your stability limit higher. But this is not the only characteristic for this parameter value. When alpha 1 is equal to alpha 2 is equal to 1/4, you have that this quantity here is equal to 1/4 by omega 2 square minus omega 1 square. And this is the value, remember, this is the value when you have the collations before. When you see before our discussion, we found exactly this value here. Look. Okay? Note that this is the square. Okay? So we have this in this case. And therefore, in this case, we have, I have a square here. Excuse me. I have a square here. Excuse me. I forget to, let me check, of course. And here we have, yes, this is a square. Okay? So square, a square. Okay. So this value is exactly the value, the old value when you have collations. But you have an additive term here for giving you lambda flutter. So lambda flutter is not coincident with lambda collations. Excuse me. You have this lambda flutter equal to this plus square plus this part, small part here, which is zeta 1, zeta 2 by omega flutter to the power 2. So what is happening? It's happening the following. In this case, your characteristic equation, remember this is S2 zeta S2 S square plus zeta plus omega 1 square lambda minus lambda, and here you have S square plus the same zeta, because this zeta is zeta 1 equal to zeta 2, because we are in the case with alpha equal to 1/2. So when you have the same damping or the both mode, your characteristic equation is the following. Determinant of this. Look. So this part, this is important, guys. Look this. This part here is common here and common here. If you call this part as S bar square, you have the same equation of the undamped system. And so you have an S bar space with the same root locus we found before. So this is the S bar real part, S bar imaginary part, and in this space we discussed already, we have the following root locus ta 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 ta. Okay? If you apply this change of variable, you have just a shift of this plane, and the shift is moving this axis in this axis, which is the actual axis of your discussion, the s-axis, imaginary s and real s. And what you can see that in your real s plane, for lambda square equal to lambda coalescence square, you have a coalescence, but you have a coalescence in the stable region. If you increase lambda after lambda coalescence, you have lambda flutter, which is after, and after means add this term here, the famous small term. So you have lambda flutter is equal to lambda coalescence plus zeta 1, zeta 2, omega squared flutter. So in this case, you have coalescence before, and look that in this case, the coalescence is not necessarily a stabilizing phenomenon. No, you have a coalescence, period. But your coalescing poles are stable now. After the coalescence, one pole goes on right, beginning unstable pole, and the other one goes on left. And so you have first this critical condition, which is not critical, the coalescence, and then this is critical because the flutter is the sum of coalescence and another term to be added. So you have first a coalescence of the mode, and then you have a distability. The very final comment is what happens in the general case. The general case is when alpha 1 is not 1 alpha. In that case, your starting point for your root locus, you start from here and here, is here. Is this, you go up, you go down, but you don't coalesce. And so you have this, and you have this. Or you may have this and this. And what about this different situation, in your opinion? Which is the parameter controlling these two different behavior? This or this? The damping. The damping. Depend on damping distribution. Is alpha 1 greater or less 1/2 on damping distribution? Okay. To be practical, I will assign to you a first relation or report on this exercise. I give you all the codes you need for performing this analysis, for evaluating analytically. I give you the code solving the characteristic equation equal to 0 for any lambda. So solution of a fourth order polynomial equation as a functional parameter. So you will be able to print and see the root locus. And you can have a direct experience on this. Tomorrow, I want to add to you just a very final point, because we studied the stability scenario of this system. Now we want to close our analysis with this response. What about, practically please, not theoretically, what about after discussing stability, what about the time response? Time response means, what about W vector as a function of time, W1 of function of time, W2 function of time, and after evaluating this, I know that in any point of my panel, in any time, the solution is phi1x by W1 time plus phi2x by W2 time, period. I want to see a stable solution and an unstable solution for assigned flow or structural condition. I want to see the stability or instability. Okay, this is the time solution. Of course, this kind of time solution is a function of initial condition only. We don't have a pushing or forcing term or input term. We have only initial solution. So this means that you take your beam, you take your panel, you impose an initial condition, any kind of initial condition, and then release. What happens? Or what happens? Release. A perturbation to initial condition. Is the perturbation limited after time or is damped? This is the stability. Okay? And after this, from tomorrow on, we will start our regular program systematically. Aerodynamic, structure, aerodynamic, elasticity, stability, elasticity response. Okay? This is just an appetizer to see several kinds of issues. Okay, thank you very much, and see you tomorrow.